So what we are going to get started with today, downright basics of quadratic expressions, equations. Some of these things you have already learnt in the past, so it would be a quick recap of those things. We would then migrate into some domains which would be kind of new to you, and get into a complete digression on quadratic equations and expressions. Fundamentally, an expression of the kind ax squared plus bx plus c is a quadratic expression. It's a polynomial of degree 2 in x. And in this case, a should not be 0. Because if a is 0, it will become a linear expression in x. It will no longer be a quadratic. B and c could be 0, but a cannot be 0 if it is deemed quadratic. Let me call this y a function of x. Now, what is meant by the root of the quadratic? Those values of x for which this would become 0. This expression would assume different values for different values of x. For two values of x, this expression will become 0. Those values of x are referred to as the roots of the quadratic. Like I mentioned to you, a polynomial of degree n in x would have exactly n roots, real or complex, distinct or coincident. This is a polynomial of degree 2 in x. It would have exactly 2 roots, real or complex, distinct or coincident. That means there would be 2 subscribed values of x for which this expression would vanish. Those are referred to as the roots of the quadratic. So this quadratic would have roots, say alpha and beta. That means the value of this function at x equal to alpha will be 0. The value of this function at x equal to beta will be 0. That means ax squared plus bx plus c, this expression vanishes at x equal to alpha and at x equal to beta. This expression will become 0 at x equal to alpha and at x equal to beta. Now, if an expression becomes 0 at x equal to alpha, if this expression becomes 0 at x equal to alpha, then very clearly x minus alpha must be a factor of this expression. X minus alpha must be a factor of this expression, right? So this expression must have x minus alpha as one factor. Similarly, this expression becomes 0 at x equal to beta. So this expression must have x minus beta as a factor. Now, when you factorize an expression, do you get an equation or an identity? You get an identity. Factorizing an expression will produce an identity. So ax squared plus bx plus c will have 2 factors, x minus alpha into x minus beta. Now, to write it as an identity, ax squared plus bx plus c. Now, can I write this equal to this? Can I write this expression identically equal to this? No, not yet, not yet. Because coefficient of x square on the left hand side is a, whereas the coefficient of x square on the right hand side is 1. Now, we want to make sure that if this expression is identical to this expression, then coefficient of equal powers of x is the same on both sides. Now, we multiply the right hand side with a. Now the coefficient of x square on the right hand side is a, and the coefficient of x square on left hand side is also a, and this could be written as identically equal to this. Now we have produced an identity. This is an identity true for all values of x. This is an identity, right? Now, if I divide by a, which I can because a is not 0. If I divide by a both sides, then I end up getting x squared plus b by a into x plus c by a equals x minus alpha into x minus beta. But what is x minus alpha into x minus beta? That's x squared minus alpha plus beta into x plus alpha beta. Yes or no? plus alpha beta. So this expression will be identical to this expression. Coefficient of x square is 1 on the left hand side, coefficient of x square is 1 on the right hand side. Coefficient of x on the left hand side is b by a, coefficient of x on the right hand side is minus of alpha plus beta, which means alpha plus beta, by equating coefficient of x on both sides, alpha plus beta must be minus b by a, right? What's the constant term on the left hand side? C by a. What's the constant term on the right hand side? Alpha beta. That means alpha beta must be c by a. So sum of the roots of a quadratic and product of the roots of the quadratic is given by sum of the roots minus b by a, product of the roots c by a, right? Now few things that you want to take notice of, which we have spelt out in our digressions on polynomials, but a quick one, and we'll establish these results later on. One, if A, B, C are real numbers, if A, B, C are all real numbers, then complex roots, if any, would occur in pairs. Complex roots, if any, would occur in pairs. That means, say, if 2 plus 3i be one root of this quadratic, then 2 minus 3i would be the other root of this quadratic. That means complex, provided ABC are all real numbers. However, if even one of them is found to be non-real, then occurrence of complex roots in pairs is not guaranteed. 2, we'll have a detailed discussion on this later on, but for the time being, take notice of this. If ABC are all rational numbers, then irrational roots, if any, would occur in pairs. What it means is that if these coefficients are all rational numbers, then if one finds that 2 plus root 3, which is an irrational number, be a root of this quadratic, then 2 minus root 3 will also be a root of this quadratic. Then 2 minus root 3 will also be a root of this quadratic. Also, check to see that sum of the roots of this quadratic is minus b by a, and product of the roots, as we figured out, is c by a, right? Now, alpha minus beta whole squared is going to be what? That's going to be alpha plus beta whole squared minus 4 alpha beta, right? Minus 4 alpha beta, which is b squared by a squared minus 4 into c by a, which is b squared minus 4ac by a squared, right? That's alpha minus beta whole squared. Now, if alpha beta are real numbers, that means if the roots are real, then alpha minus beta would be also real, and the square of a real number will always be non-negative. Alpha minus beta whole squared will always be non-negative. If alpha and beta are both real numbers, then difference of their squares, square of their difference would always be non-negative. That means b squared minus 4ac by a squared would always be greater than or equal to 0, which would mean b squared minus 4ac greater than or equal to 0. Yes or no? That means if b squared minus 4ac greater than or equal to 0, or rather if the roots are real, then b squared minus 4ac greater than or equal to 0. In fact, what you have already learnt in the past, and again, you know, these things would support what you have learnt in the past. If alpha is equal to beta, that means if the roots are equal roots, that is alpha is beta. If alpha is beta, that means alpha minus beta whole square is 0. If alpha is beta, that means b squared minus 4ac will turn out to be 0. In fact, this number b squared minus 4ac is an important entity. We call this as the discriminant. B squared minus 4ac is referred to as the discriminant of the quadratic. And again, reiteration of some of the things that you have learnt in the past. If discriminant is greater than or equal to 0, rather if discriminant is greater than 0, this would mean roots are real and distinct. If discriminant is equal to 0, roots are real and coincident. Roots are real and coincident. At least roots are real. If a, b, c are real, then the roots would be real. If discriminant is less than 0, then roots are complex. Assuming a, b, c are real numbers. Assuming a, b, c are real numbers. So this was a quick recap of things that you've already learnt in the past. Now, notice y equal to fx equal to ax squared plus bx plus c. The graph of this is a parabola. The graph of this is a parabola whose axis is parallel to the y-axis, right? Whose axis is parallel to the y-axis. We've learned this in parabola, right? Y equal to a quadratic in x. If you plot it in the xy plane, it's going to give you a parabola. That means now this graph could be, in principle, either a parabola like this, or it could be a parabola like this. Now, just to clarify matters here, for any given x, this y represents fx. This y represents fx. For any given x, this y represents fx. That means this point on the parabola has coordinates x comma y, where y is fx. For any given x, f of x means the value of this expression at x. The value of this expression at x. That's going to give me fx, and that's plotted in the y direction. The f of x's are plotted in the y direction, assuming different values for different values of x. Now, see, like I told you, there are two cases. When I plot y a function of x versus x, I could have had a parabola which opens this way, and it's called an upward opening parabola. It's an upward opening parabola. Whereas y equal to fx versus x this way. In both cases, the axis is parallel to the y axis. But this is a downward opening parabola. This is a downward opening parabola. I then want to figure out, by looking at this expression, whether when I plot y versus x here, y equal to fx versus x here, whether I'm going to get an upward opening parabola or I'm going to get a downward opening parabola. Now, the way to determine that is not difficult. See, this expression y equal to fx could have been written as, if I took x square common, x square into a plus b by x plus c by x square. Yes or no? Yes or no? Now, say two cases, a positive, one case, right? A positive, one case. As x tends to plus or minus infinity, what happens to b by x and c by x squared? B by x and c by x squared would tend to 0, right? What happens to x square? If x tends to plus minus infinity, x square would tend to plus infinity. X square would tend to plus infinity. Now, if x square tends to plus infinity, these two go into oblivion, then a into x square would tend to plus infinity. So, which means y equal to fx would then tend to plus infinity. Yes or no? Because a is positive, these two numbers vanish. A into a very large positive number would be a very large positive number. So, y equal to fx, fx tends to plus infinity. That happens for a greater than 0. Now, very clearly, see, if the parabola is upward opening, say something like this. As x becomes larger and larger and larger and larger, what happens to y? This is y, which is a function of x, the value of the quadratic at x. As you keep moving to the right, that means as x becomes numerically larger and larger and larger, what happens to y? Y tends to plus infinity, right? Also, do you see that this is x, this is y, which is fx, right? As x tends to minus infinity, move in this direction, fx will tend to plus infinity. That means in this graph, as x tends to plus infinity or as x tends to minus infinity, y tends to plus infinity. That means, as x tends to plus or minus infinity, y tends to plus infinity for this case, and we can then conclude that this must be the case for a greater than 0. That means if a is greater than 0, then what we get is an upward opening parabola. That means in this quadratic expression, if a is positive, y equal to fx versus x is going to be an upward opening parabola. How about it, right? Similarly, if a is less than 0, this is case 2, if a is less than 0, as x tends to plus or minus infinity, same way, b by x and c by x squared would tend to 0. Right? X square would tend to plus infinity. If x tends to plus or minus infinity, x square would tend to plus infinity. These two would vanish. So a, if it's a negative number into a very large positive number would be a very large negative number, right? A is negative, x square is large and positive. So a into x square would be large and negative. So a into x squared, which is what eventually is is the leftover term would tend to minus infinity. That means y, which is fx, which tends to minus infinity. So if a is less than 0 and as x tends to plus minus infinity, y tends to minus infinity. So the graph of now if you check the downward opening parabola, y equal to fx versus x, look at this. This is x, this is y, which is f of x, the value of the function at x. As x tends to plus infinity, what is happening to y? Y is tending to minus infinity, isn't it? It's a negative number and is becoming larger and larger and larger. So as x tends to plus infinity, y tends to minus infinity, as you can see. Look at this case. Look at this case, x. This is y, which is fx. As x tends to minus infinity, what is happening to fx, which is y? That's also tending to minus infinity, which matches with this case. So the downward opening parabola is a less than 0. The downward opening parabola is a less than 0. Yes or no? So right away I can say if a is positive, the graph of y equal to fx is going to be an upward opening parabola. If a is negative, the graph of y equal to fx is going to be a downward opening parabola. Right? Now, so fx versus x, this is an upward opening parabola, and this is for a positive, and y equal to fx versus x, this is going to be a downward opening parabola if a is less than 0. Now this is the axis of symmetry. This is the axis of the parabola in this case. This is the axis of the parabola in this case. Right? These are values of x. See, this is a point, this is a value of x for which y is becoming 0. Y is becoming 0 means this is becoming 0 for a value of x which is alpha. At x equal to alpha, y is becoming 0. Also at x equal to beta, y is becoming 0. So the point where the graph crosses the x-axis or pays tribute to the x-axis would be the roots. So in this case, alpha plus beta must be the roots of the quadratic. Alpha plus beta must be the roots of the quadratic. Alpha and beta are the roots of the quadratic. In this case, this is the point where the quadratic becomes 0, alpha and beta. So alpha and beta in both these cases are the roots of the quadratic. Now, this is the axis of symmetry. This is the axis of symmetry. And it must lie exactly halfway between alpha and beta. That means, if this point is x equal to x naught, and if this is a point on the axis of symmetry, in both cases, this is x naught, then x naught must be alpha plus beta by 2, halfway between alpha and beta, but alpha plus beta is minus b by a, so this must be minus b by 2a. In both cases, x naught is minus b by 2a. This line therefore is y equal to x naught. I'm sorry, x equal to x naught. So this line which is parallel to the y-axis is x equal to minus b by 2a. So axis of symmetry for such parabolas would be x equal to minus b by 2a. Line parallel to the y-axis. Yes or no? Now, suppose a is positive. Suppose a is positive. Then the graph of this is going to be an upward opening parabola. It could be like this, for example, alpha, beta. In this case, alpha and beta are the roots and they are real and distinct. They are real and distinct. And therefore, this must be the case where discriminant is strictly greater than 0. Right? Or we could have had, so in all these cases, A is greater than 0. Or we could have had an upward opening parabola oriented as follows. This is alpha equal to beta. Roots are real and equal. Roots are real and equal. And therefore, the discriminant of this must be equal to 0. Discriminant of this must be equal to the 0. In this case, the x-axis becomes a tangent to the curve. The x-axis becomes a tangent to the curve. The parabola touches the curve. In this case, the parabola cuts the curve. Or the third case is y equal to fx versus x. Could be like this, in which case fx, that is the quadratic, is not becoming 0 for any real value of x. That means the graph is strictly above the x-axis. This must be the case where no real roots, and therefore this must be discriminant less than 0, no real roots of the quadratic. Right? So this is in this case the graph is strictly above the x-axis. The graph is strictly above the x-axis. In all these cases, the axis of symmetry will still be x equal to minus b by 2a. This is d less than 0 and a greater than 0 for all these cases. Do you also realize that if a is greater than 0 and d is less than 0, that means if a is greater than 0, it will cause the parabola to be upward opening. And in addition, if d is less than 0, there would be no real roots, which would cause the graph to be strictly above the x-axis. Then for any given x, this is the value of fx, the corresponding y will be fx. Fx turns out to be positive for all real x. In this case, fx is greater than 0 for all real x, So if d is less than 0 and a is greater than 0, then fx, that means the quadratic expression will maintain the same sign for all real x. If a quadratic expression has no real roots, and if a is greater than 0, then the quadratic expression will be positive for all real x. Yes or no? Yes. However, if you find that the quadratic expression, see, is positive for some x and it becomes negative for some x, that means if it happened to change sign at least once, that means positive somewhere and negative somewhere, then you can be guaranteed that it must have two distinct real roots. Right? So, an upward opening parabola with no real roots will be positive for all real x. However, if a quadratic has distinct real roots, then it will be positive somewhere and it will be negative somewhere. If an upward opening parabola is found to be negative at least one value of x, then positive anyways it will be for a large number of values of x, and it will guarantee existence of real roots. Right? So, one thing for sure, if d is less than 0 and if a is greater than 0, then fx will be greater than 0 for all real x. It will maintain the same sign. Right? And conversely, if you find that fx is greater than 0 for all x, you can conclude, 1, it's an upward opening parabola, 2, discriminant is less than 0. Right? Now, similarly, if a is less than 0, then it's going to be a downward opening parabola. Something like this. Alpha, beta, real and distinct. If this be the disposition of the parabola, discriminant must be greater than 0 for such a parabola, because alpha and beta are real and distinct. Or we could have had the parabola becoming a tangent to the x-axis and downward opening. In this case, the x-axis becomes a tangent. Roots are real and equal. This is discriminant equal to 0. Or we could have had y equal to fx versus x. This, all of this is a less than 0. Do you realize no real roots in this case? No real roots. This is equal real roots. And no real roots, that means this must be the case where d is less than 0. And again, the interesting thing is that for any given x, fx, the quadratic expression, maintains a negative sign for all real x in this case. So this is the case where fx is less than 0 for all real x. And conversely, if fx is found to be less than 0 for all real x, you can draw two conclusions. One, it's going to be a downward opening parabola, that is a is less than 0. Two, the discriminant is less than 0. Yes or no? Right? Now, the case of no real roots, that means for an upward opening parabola, d less than 0, a greater than 0, and you find that for any given x, fx is greater than 0, right? No real roots for an upward opening parabola, no real roots for a downward opening parabola. This is a less than 0, discriminant less than 0, fx is less than 0 for all real x, right? In both these cases, if d is less than 0, see, in both these cases d is less than 0, no real roots. The parabola doesn't pay tribute to the x-axis. A into fx is positive here, and a less than 0, fx less than 0, that means a into fx is positive. That means if you find that a into fx is positive, that means a and fx must be of the same sign. If you find for a quadratic expression fx, a into fx greater than 0 for all real x, for all real x, if you find a into fx greater than 0, then you can conclude that a and fx must be of the same sign. Same sign for any x belonging to the set of real numbers. That means you can conclude that discriminant is less than 0. That means a into fx positive, it would either be this case or this case, if it happens for all real x, right? So both these cases are about a into fx greater than 0. Now, see, one very simple observation. The quadratic expression, if it had roots alpha and beta, if this quadratic expression had roots alpha and beta, right, then this could be factorized as ax squared plus bx plus c could have been written as a into x minus alpha into x minus beta. That's how you could have written this, right? Now, if discriminant is equal to 0, then alpha will be equal to beta. If discriminant is equal to 0, then alpha will be equal to beta. And this will then turn out to be a into x minus alpha whole squared, which is a perfect square. Which is a perfect square. That means if the roots of a quadratic are equal, if the roots of a quadratic expression are equal, that means if discriminant is equal to 0, then the quadratic must be a perfect square. That means for a quadratic to be a perfect square, what is required is the discriminant to be equal to 0. Yes or no? Right? Fine. So this brings us to some basic understanding of the quadratic expressions. From this point, in the next session, I'm going to give you a few more remarks, few additional remarks on quadratic expressions and how to deal with problems related to quadratic expressions. This much for today. We'll catch you in the next class. Take care. Bye-bye.